Well, we have 30 minutes and we have a lot of talk to cover, so let's get started right off the bat. Okay, so in this talk, we're going to be looking at some topics in computer science, and we're going to be looking at them through the eyes of software developers and engineers. So we're going to see how might knowing a little bit of computer science help us out when writing our code, designing our applications, but also why might some of these topics might not be that relevant to us in our day-to-day lives. My name is Andy Andrea. I've been working with Rails for about 8 years. I graduated with a degree in computer science in 2014, and since then I've been working at a small company in Durham, North Carolina called SciMed Solutions. We're a consultancy, so we make a lot of different types of apps. I've worked on a lot of types of projects, including some with some very new and some with some very old versions of Ruby and Rails. I want to be clear, though, that I am a software developer. I am not an academic or a computer scientist, so that's the vantage point that this talk is coming from. A couple things to know before we get started. If I say CS, that just means computer science. If I say space, we're talking about memory. And if we're talking about logarithms, we'll get into a little bit of math here and there. Assume that we're working in base 2. Again, a logarithm is basically the opposite or the inverse of a power or exponent, if you haven't used them in a while. Also, I can't quite cover all of computer science in 30 minutes, which is good for me. I traded in all of my CS textbooks for a Nintendo Wii U, which tells you about how much I valued them. It was a Wii U of all things. But because of that, I've put some magnifying glass emojis at the bottom of certain slides that have things you can Google, things you can look up. Might be things that I cut from the talk or just related topics. The first thing that we're going to talk about today are numbers, specifically starting with everyone's favorite bug that's not a bug, floating point arithmetic. It's a common enough issue where you can start typing in a number like this into a search engine and it'll actually autocomplete for you. Though, full disclosure, it was kind of annoying. I went to Google and I went to DuckDuckGo and none of them had it as like the top suggestion. So if nothing else, even if this talk like really bombs, I'm pretty sure I'll be the only talk in all of RailsConf that has a screenshot from Microsoft Bing. So that's something, right? But to answer why this is happening, why 0.1 plus 0.2 doesn't equal 0.3, let's actually look at numbers. So we're used to thinking of numbers as having a representation like 7053 that's equal to a value, 7053. But we know just by looking at this number that the 5 in there doesn't mean literally 5, like the number of fingers I have on a hand, but it's 50. The 7 isn't just 7, it's 7,000. And you can actually break down the representation of a number into an equation where the individual digits are multiplied by successive powers of 10. So our rightmost digit is 3 times 10 to the 0th power, or 3 times 1. And then 5 times 10, that's where we get our 50, so on and so forth. And the thing that's important about this, it's not the powers or the addition or anything, but the 10 itself. And that's because 10 is our base. We work in a base 10 or decimal system when we typically do math. But computers use binary, base 2, which is a different base. So in base 10, we have 10 different characters that we can use to represent a number, 0 through 9. And when we run out of those characters, then we have to start adding new digits. In binary, we just have 2 digits, or 2 numbers, 0 and 1. And then once we run out of those, then we have to start adding new bits, or binary digits. So 0 and 1 look exactly the same in binary as in base 10. But then as soon as we get to 2, you can see we have to start adding new bits. If we're working with a larger base, like base 12, then we have more characters that we can use. So 0 through 9 look the same as in base 10. But then once we get to 10, then we still have the character A we can use. 11 would be B. And then when we get to 12, we get to our 1, 0 value, which looks to us like 10. For the rest of this topic, though, we're just going to be looking at binary mostly, comparing it to our usual base 10 system. And like we saw a couple slides ago, binary also can be broken down into an equation, but now we're multiplying by powers of 2, not by powers of 10. And so 1, 1, 1, 1 in binary can add up all those powers of 2. It gives you what we typically call 1, 5 or 15, which is very different than 1, 1, 1, 1 in base 10, 1,111. So far, we've just been talking about whole integer values, but fractional values, decimals, look very much the same. When we get to the right of our decimal point, then instead of multiplying by a positive power of 10, we just keep going down and start multiplying by negative powers of 10. And a quick reminder that a negative power of a number is basically the same thing as 1 divided by the equivalent positive power. So 10 to the negative 1 is 1 divided by 10 to the 1. And if any of this math isn't quite tracking for you, do not worry. This is not the point of the talk. It's just meant to, again, give some extra context. But just like we have negative powers of 10 in decimal, when we're working in bicimal or binary decimals, we have negative powers of 2 when we get to the right of our bicimal point, or a more base agnostic way to refer to it is a radix or radix point. So if we want to represent the number 6 3/8, 6.375, then we need a 1 in our bit corresponding to 4, added to a 1 in our bit corresponding to 2, that gives us 6. And then to get 0.375 or 3/8, that's 1/4. So we need a 1 in our 2 to the negative 2 bit, added to 1/8 to the negative 3. Again, if this is not tracking, don't worry. This is just extra context. We know from base 10 that there are a lot of fractional values that can't be represented in a finite number of digits, like 1/3. We usually just say, oh, 33% or 0.33, but that's not entirely precise. It's an infinite number of 3s after the decimal point. One kind of cool thing is that if we switch our base, then suddenly numbers that maybe needed an infinite amount of space, whether that's paper or memory, can now be represented in a finite number of digits, bits, whatnot. So 1 divided by 3, if we're working in base 3 math, is literally 0.1. That's exactly the value 1 divided by 3. We're not missing out on anything by just having that one number to the right of the radix point. However, the inverse also holds true. So in base 10, 0.2 is a very, very easy number for us to reason about because it's just 0.2. But if we try to convert that value into base 2 binary, it's actually an infinitely repeating number, just like 1 divided by 3 is in base 10. It's 0.011, just infinite number of times. And so if we want to store that or visualize it perfectly, accurately, and precisely, we need an infinite amount of space, which typically we don't exactly have. So a really simple way that we can get around that is just we try to get close and we pick a number of bits or digits and then we truncate or round off. And this is essentially what's happening with our floats in Ruby and a bunch of other programming languages. So there's a little trick you can do in Ruby to see the underlying value corresponding to a particular float. And so here you can see that 0.1 is pretty close to 1/10, but it's slightly larger. Same thing for 0.2. It's a little bit bigger than the actual 2/10 value, but 3/10 is actually slightly smaller. The closest we can get to 0.3 in this system is slightly smaller than actual 3/10. And so if you add a number slightly larger than 0.1 to a number slightly larger than 0.2, it's going to give you a number slightly larger than 0.3, which won't be equal to a number slightly smaller than 0.3. So this is the explanation of what happened on that first slide. There are a couple of other ways that we can do this if we really care about our precision. One way is rather than saying 1 divided by 3 and trying to turn that into a decimal value, we can just say, no, it's just 1 divided by 3 and store it as an equation where you don't have to worry about the actual division and all those infinite bits and digits. And we basically have this in Ruby with the rational class. So here you can see the rational representing 1/10 added to the rational representing 2/10 does in fact equal the rational representing 3/10. Can be a little bit hard to read though. For me personally, this example on the bottom, I can't even really tell what order of magnitude that is just by looking at that division. It means very, very little to me. But we have our precision back at the cost of some performance. We have to store that number on the top, the numerator, store the number on the bottom as well. So it slows things down, takes up a little bit more memory. For our Rubyists in the room, which is probably most of us, we probably use big decimal rather than rational or float when we care about precision. And I'm not going to get into how big decimal works under the hood, which is pretty interesting. So you can, of course, look it up on your own if you want. But it gives us that precision back. So 0.1 plus 0.2 equals 0.3. That's great. Again, though, it does have some costs in terms of performance and in terms of memory. There are a few other issues that we can run into as software developers when we're dealing with numbers. These are kind of dependent upon what programming language you're using, sometimes even what platform you're using. We're not going to cover them too much in the interest of time and getting into more interesting things that aren't math. But if you're dealing with very large numbers, then of course you might need a very large amount of memory. Negative numbers can be represented in such a way where you might accidentally get a negative number when you add two positive numbers together, which I've never seen math that works like that before. Also, overflows and underflows are things that you can run into in certain programming languages. Ruby is pretty good about this stuff, so we don't have to worry as much as if you're programming in, say, C or another low-level language. So why do we care? Why have we been looking at all these annoying zeros and ones and binary? Well, first off, knowing when to use floats, when to use decimals is very handy if we have to deal with money and you're using a float. And suddenly you have these rounding errors and people try to pay a bill and maybe it says they didn't pay the bill. So it can be very important for us to consider that precision. But at the same time, if we care more about performance and we're willing to have a lack of precision, then maybe a float is the thing to use. On the last slide, we talked a little bit about some of the other issues like overflows, underflows. In some languages, like even in JavaScript, if you're using very, very large numbers, then math can just kind of break down at a point where like a number plus another number still equals that first number. You get kind of weird. That said, I don't know about you guys, but I don't think in terms of zeros and ones. I don't use binary in my day-to-day work. I don't know that I've really thought about binary much since I've been programming. As Ruby developers, we're using a very high-level language, and kind of the point of that is to hide and abstract a lot of the stuff away so we don't have to worry about it and we don't have to think about it, which is great because I don't really like thinking about it that much. And the thing that I think is important to remember is we can use something and use it well and use it correctly without necessarily knowing how it works under the hood perfectly. So that covers part one. Part two is algorithms. I personally think this is a little bit more interesting because there's less math, if nothing else. So to start with a shared definition, the reason that I chose this definition in particular is that second word, process. Sometimes we can think of algorithms as tied to code or even tied to computation and computers. But if we're willing to broaden our definition a little bit, we can actually get a lot more power from knowing algorithms. And we're going to cover that a little bit later. Here, we have a bunch of algorithms, implementations of algorithms, all trying to do the same thing, sorting data. And so here you can see that some appear to be doing a lot better than others. Anybody play Mario Kart in the room? Yeah, okay, good, some nods, good, I'm relatable. It's important after talking about binary for a long time and admitting to using Bing. But I think that sorting algorithms here are kind of like playing Mario Kart. Like some people are really, really good. They like start off and they're like in first place the entire time. Like quick sort in our middle here is doing pretty well. And then there are people like me who are not very good at Mario Kart and are like tripping over their own banana peels. And that's kind of like our bottom left bubble sort. You can tell it's moving towards the finish line, but it's not really getting there that fast. If quick sort is like a race car, then bubble sort in this example is like a little dachshund with its tiny little legs like chasing after it. Very cute, but like, it's not really doing the job that great. So if we have some that seem to perform so much better, why do we have so many? We have a lot more sorting algorithms than just these 9. And here, if anyone is having trouble differentiating colors, quick sort here are the sort that was working pretty well on our last slide. Has some metrics that are green, so that's good, but also has some that are red and one that's yellow. And this is because just like some people might be really good at certain maps in Mario Kart, different sorting algorithms are better at different types of data. So if you have data that's very, very randomized versus data that has a lot of duplicate values versus data that might come already almost sorted, different sorting algorithms can handle those with different degrees of effectiveness. To understand what these colors and columns mean, we have to know a little bit about how algorithms are analyzed in terms of their complexity. So if you've ever heard of big O notation, that basically corresponds to our worst case column here. So In other words, quicksort would have big O of n squared time complexity. Time complexity is roughly going to be synonymous with like runtime of actual implementation, or the number of executions or operations that your CPU has to go through in order to execute your code. Similar notations like big omega, which is our best case, big theta, which is our average case, also exist. They have formal definitions. The average time isn't just like you implement it and run it a bunch of times and take the mean. It has a mathematical definition, but we're just going to stick with our worst case big O notation moving forward. The other thing that's really important here, the meaning of all these n's. So n is the size of our input. So for a sorting algorithm, it's basically the size of the data that we're trying to sort, like the length of an array. And so when we say that quicksort is big O of n squared, that means that in the worst case scenario, as we increase the size of our input, the time complexity or the number of executions is going to be increasing a lot faster. So this is not very good. Ideally, if we increase our data a little bit, then the runtime of our code would also increase just a little bit. But for things like n squared, it increases a lot more rapidly, which can be a bad thing for us. A couple other things in addition to like n log n and n squared that we've seen so far, different time complexities you might run into. You can see just from this graph, some grow a lot more quickly than others. And this can have real performance implications for your implementations of your algorithm. If it shoots up really fast and you're going to be dealing with a lot of data over time, then your code might not scale that well. A really good time or space complexity, we're just going to be talking about time complexity moving forward, is constant time, or big O of 1. And you can see it doesn't have an n in there, so that means that it's going to take roughly the same amount of time to execute regardless of your input. So it scales essentially perfectly. A really bad complexity, on the other hand, would be factorial time. And exclamation point, factorials are just a number multiplied by all smaller numbers in itself. So 4 factorial would be 4 times 3 times 2 times 1. And that just shoots up super quick. I had to take it off this graph because it made everything else basically just like smushed together. But now that we've talked a little bit about different complexities, what do they actually look like in terms of an algorithm or code? And the handy thing about time complexity is that you can get a rough sense of it by looking roughly at how many lines of code get executed. This isn't exactly precise, and for reasons that we'll talk about in a little bit. But here, this is that constant time. It doesn't really care about the size or the length of our data. It's just one line of code that gets executed one time. So big O of 1 in our worst case. A slightly more complicated example would be big O of n, or linear time. And so our first line of code here, our puts, that's just constant. Again, it's 1. It doesn't look at the size of our array or anything. But then when we get within our reduce, we have 2 lines of code. Each of those will get executed for every element in our array. So n times, meaning that we have 2n, or 2n plus 1 across the entire method when we're including that puts. However, in big O notation and similar notations, we drop coefficients and constants and lesser terms. That's because we're usually considering how our algorithm performs as n approaches infinity. And so when we have infinity and we're adding 1 to it, that's just infinity. It doesn't really change things. Similarly, n cubed plus n squared will have a much smaller effect, so we just drop it. Coefficients are a little bit weirder, like that 2 in our 2n. And that's because when you're implementing your code and running it in different environments, different things might happen. Like if you're working with very fast memory versus very slow memory, or you're running Ruby 1.8 versus Ruby 3.1. So these things all kind of just make the coefficients less precise and valuable, so we just get rid of them. Okay, so we've talked about how algorithms are analyzed in terms of their complexity. Let's design an algorithm from scratch. So if we have a very simple application, say a bookstore or a library, we have a list of books in an array, they all have a title, we've got them all sorted alphabetically because we're programmers and we're particular about this kind of stuff. And let's say we want to find a particular book by its title. So let's say the pragmatic programmer happens to be the last one in our list here. Very simple way that we can get that is books.find in Ruby. Very readable, Very simple, gets the job done. You can see here from putting a put statement in our find block that it goes through every element in our array, looks at it, says, okay, this is not the one you're looking for, until it finds the book that we want and returns it. So this is perfect. It works. If we literally have like 8 books, it'll run perfectly quickly. But we can do a little bit better than this if we leverage the fact that all of our data is sorted, again, by title. So if instead of starting right at the beginning and looking at clean code, if we hop in the middle and look at practical object-oriented design in Ruby, compare that to the book that we're looking at, or looking for, the pragmatic programmer, we know the P in practical comes before the T in the. And so since everything is sorted alphabetically, since the P comes before T in the alphabet, that tells us that the book that we're looking for has to be later in our array. And because of that, we don't even have to look at the first half of our array. We know that's not the book that we're looking for. And so then we can just continue jumping forward and we see, okay, the M in mythical, that's still before the P in pragmatic. So we can discard that one as well as the other Ruby under microscope that we had. And we found our book. And we found it pretty fast. We didn't have to look at everything in our array to get what we wanted. And this is a really classic algorithm called binary search. And we actually have access to a binary search method in Ruby on arrays and ranges. It's called bsearch. And looking at the output from our puts that we have in our block, it's exactly what we saw in the last couple of slides. It just looked at 3 books and found the one that we wanted, rather than having to go one by one by one. There are a couple gotchas here. Of course, if our data wasn't sorted, we couldn't make those assumptions about it having to be later in the array based on it being later in the alphabet, because we don't really know anything about how our structure is set up. Also in Ruby in particular, if we had swapped the order of book.title and the pragmatic programmer string with our comparison operator, then it would have failed. That's just because the comparison operator requires things to be order dependent, so returns -1, 0, 1. If we wanted to have them in the other order, we would have to have reversed the sort of our books first. Speaking of binary search, there's another great implementation of binary search that we have access to in our typical Rails stack, and that's a command within Git called git bisect. If you look at the man page, it literally says we use binary search. And so git bisect can be used to find a commit that introduced just about anything, a bug, a failing test. So for example, if we wanted to find a failing test, we know the test worked on version 1.0 of our app, and it's failing on the head of our current branch. We tell that to Git, and then it jumps back in time to a commit about halfway in between the two. And then it's up to you as the programmer to run the test and then tell Git, okay, this commit is good or this commit is bad. And this, I think, is super, super valuable for us to think about, because the algorithm, not all of it is happening in code or even on our computer. It needs us as human beings to tell it, okay, this is good or this is bad. And so if we can think of algorithms as a higher level topic than just a computational resource, we can get a lot more out of them. Like if you go to a bookstore, say Powell's here in Portland, and you're looking for a book by Jules Verne, you're probably not going to the first bookshelf and looking at every single book. You start more towards the end of the books, and then you see, okay, maybe I have to jump back a couple more bookshelves, and then you narrow it down without literally looking at every single one. And so that's kind of something analogous to binary search that we can use in real life, which can be really, really helpful. So having talked about algorithms, great thing about them is if we know them, we can use them. Whether or not that means we're writing the algorithms ourselves, or we can use something like Ruby's bsearch to speed things up a little bit. Also, data structures are oftentimes analyzed with that same big O and similar notations. So there might be like linear access time for a data structure or constant write time. Also, the great thing about algorithmic complexity in big O is that it forces us to think about our code in terms of how it will scale with our data, which is increasingly important because our data is getting bigger every day. I mean, big data has become an increasingly large buzzword. It's like data warehouses, data lakes, all that stuff means that we have to consider how our code will work with larger data sets. Also, having a great shared language with our teammates and coworkers. So if you're in an architectural planning meeting or doing code review, you can say, hey, this would be a great place to use binary search, rather than saying, well, hey, we could like sort our data and like cut it in half a bunch of times. Like, I don't really know what that means, but binary search tells me exactly what you want me to know. At the same time, though, algorithmic complexity is oftentimes not our number one bottleneck. Things like reading and writing to a database or looking at the file system, sending requests over the network, intrinsically take a fairly long time. So if we're super focused on just looking at the complexity of our code, we might miss out on those more important bottlenecks. Also, algorithmic complexity is a pretty bad metric as far as metrics go. It's nothing like getting benchmark data or real world data. And part of that is because of all those things that we said that we're discarding, the constants, the coefficients, the 2 and the 1 and the 2n plus 1. In real life, those things matter. And so while algorithmic complexity in computer science would tell you that linear time is always better, if you have like something that's like a trillion n versus like 0.01 n squared, for a lot of sizes of data, that second algorithm will probably perform better for you. Also, it can be really hard to actually measure algorithmic complexity very accurately in Ruby because so much stuff is happening under the hood. You have the network calls, active record, all that stuff. So just looking at your code can not really give you the greatest sense of what happens, which is why we use things like benchmarking or profiling data. Also, a lot of our tools already have a lot of this optimization built in for us. So if we want a really quick sort, we don't have to write our own quicksort. In fact, if we tried to write our own quicksort in Ruby, it definitely won't be as fast as the quicksort provided by Ruby. And again, this is one of the great things about using a high-level language like Ruby. So we've looked at a couple topics. Taking a step back, why do we care about computer science? Well, the big one, the super annoying one, in my opinion, does come up in interviews. I'm sure we've all heard the horror stories about like whiteboarding inversions of binary search trees. Ugh, yeah, gross. But luckily that seems to be decreasing a little bit, and I am going to talk about this on the next slide as well. We mentioned shared language with our teammates, increasing the understanding of some of our tools can be very helpful. And of course, if you're ever working on lower level work, like hacking on Ruby, or doing something more academic like advanced graphics, having more of that academic computer science knowledge can certainly be helpful. At the same time, though, it's important to remember that related as they may be, software development and computer science aren't the same field. So if we focus too much on learning academic theory and not enough on learning good practices or design patterns, then you might not be growing as quickly as you would like. And also, if you're trying to understand how everything at a lower level than the code you're writing works, well, first you have to understand Ruby, then you have to understand C, then you have to understand logic gates and like electricity, and like suddenly you're not meeting your deadlines because Amazon hasn't like overnighted an electron microscope and you haven't finished reading like a theoretical physics textbook. So it's just like this endless rabbit hole, and while it can certainly be helpful, you can just end up losing a lot of productivity if you focus on it too much. And on the note of hiring, I'm sure we've all heard the memes of job listings that are like requires 20 years of experience in like React or something that's like 2 months old, right? And so there's that, but then at the same time, whenever I see those job postings that say like computer science degree required, I know that whoever wrote it was not in my computer science department. I had so many professors say like, okay, well, I'm gonna send you some homework today, you're gonna code. I don't know how to code, so don't ask me any questions. I'm like, how are you supposed to learn, right? And also in my program in particular, sorry about that, very theoretical program, you could take an intro to object-oriented programming class your first semester and then never program again. Like, so the idea that you're like going to be a great software developer when you don't have practical experience like you would have from, say, a boot camp is kind of silly. The most important reason why I think, though, that we don't need to learn or to know computer science is because you can learn it. A lot of it you'll just learn naturally on the job. If you see 0.1 adding 0.2 does not equal 0.3, you're gonna Google it, or I guess Bing it if you can't find the thing you want. But you don't need to pay tens of thousands of dollars or listen to the same professor tell the same jokes every semester about how he has a friend that has a yacht that he financed by selling $400 textbooks, so he named it the SS Undergrad. Yeah, it was like, yeah, too many classes where I heard that same joke. But yeah, you can learn this stuff however you want. If you like self-study, if you want to have a mentor, hopefully, like I've demonstrated today, if you go to a talk, maybe you can learn a little bit about it. So thank you all for coming. Also a big thank you to all of my past and present coworkers and mentors for helping get me here. And a shout out to Carrie Miller for some great advice in prepping this talk, and to Billy Fry for helping me cut it down to time.